Hello, class. Today we're going to look at section 3.6, rational functions. And my goal is that as you watch this video, you make your own notes. The notes from the textbooks are right here, and I'm going to kind of go through each and every one of them. And as I do that, I will also be making some supplementary notes on the side so that you can add that to your note taking. Okay, so let's just delve into today's topic. Today's topic is rational functions, and the question is, do you know what a rational function is? If you cast your mind back, we looked at what is a rational number. If you think way back in 320, when we're dealing with the real number line system, we discovered that a rational number is a number that can be written in the form P over Q, or if you think about it as a ratio. So, in that regard, what can we say about rational functions? It looks like a rational function is a function that is made up, it's a fractional function. Let's put it at best like that. It's a fractional function where, well, let's look at what the definition is from the textbook. So it says a rational function is a function of the form P of x divided by Q of x, where P and x, when P and Q are polynomials. And in this case, what we're going to assume is that there are no common factors between P and Q. Later on, we'll look at how we handle common factors in our polynomial. But for now, a rational function is strictly a fraction where the numerator is a polynomial and the denominator is a polynomial. It's as simple as that. Now, what I want to try and do over here is I'm going to collapse this page. So that's page number 2, 3, 4, 5, 6, 7, 8 to page number 8. I'm going to just try and collapse it into one single problem so they can make sense to you. But if the textbook makes sense to you too, that's perfectly fine. But I'm going to try and collapse these slides into one big problem and kind of solve it from there. So, one of the basic block functions that we looked at was 1 over x last term. And so we're going to start off with some prior knowledge, something that you already know. So some things that we can find about this function here is we can look at the domain. So what's the domain? The domain is x belongs to our real numbers except 0. I hope that wasn't too hard to find. And then we can also examine or look for the x-intercept, which is when y is 0. So in our case, we have 0 is equal to 1 over x, which gives us 0 is not equal to 1. So we have no x-intercept. And then we have y-intercept, which tells us that's when x is 0. So in our case, I'm looking at y is equal to 1 over 0, which is undefined. So again, we have no y-intercept. So that's just coming from our prior knowledge. We could find the domain, we could find the x-intercept, we could find the y-intercept. Now, we could also do something that we did last term. We could look at the end behavior. So when we looked at end behavior last term, we were trying to do, as x approaches positive or negative infinity, we wanted to find out what's happening to y. That's what we're interested in. So we're going to kind of do the same thing with this function over here and develop some big ideas to help us handle end behavior when we have rational functions. So let's examine x approaching positive infinity. Now, when I say positive infinity, I hope you are thinking along the lines of really, really big numbers. So, for example, I'm thinking of 1,000. What's f of 1,000? Let's see what the behavior looks like. I have 1 over 1, 2, 3,000. That would mean I end up getting 0.0001. No, that's not right. 0001. All right. Now let's try another one. Let's try 10,000. I get 1 over 10,000. I end up with 0.1231. If I try f of 100,000, I end up with 0.12345. So you could see what the trend that is happening over here as x is getting bigger. Looks like all the y values are getting smaller, approaching 0. So we can say that as x approaches positive infinity, y is approaching what? Is approaching 0. All right, let's call this case 1. Now let's look at case 2. When x approaches negative infinity, let's see. So again, think about a big negative number. So I'm thinking of negative 1,000. That's 1 over negative 1,000. We end up with negative 0.001. If I try negative 10,000, get 1 over negative 10,000. I get negative 0.0001. If I do f of negative 100,000, get 1 over negative 100,000 is equal to negative 0.12345. You can see again that y is getting smaller, approaching 0. So again, we can answer this question now that as x goes to negative infinity, y is approaching 0. From a graphical perspective, I hope this makes sense to you. That what we're trying to say is that as x approaches positive infinity and as x approaches negative infinity, it looks like in both cases we are approaching the y value 0. So if this was the line 0, then we're saying that as you sketch, well, let's use that. That's much better. We can all see. All that is saying is that as you sketch this graph, the y value looks like it's getting closer and closer. The end behavior, the graph, is looking like that or like that. As you get closer and closer to positive or negative infinity, the y value approaches 0, the line 0. Okay, so you can clearly see that we have a line situation over here. So the line y equal to 0 is a horizontal asymptote. We call HA. All right. And later on, we'll describe what a horizontal asymptote is. But pretty much, it is a line that, as you examine the end behavior, that is how the graph of that function is tapering towards. Okay, so that's what we call a horizontal asymptote. Now, let's look at another scenario. So we figured out the x and the y intercept, we looked at the end behavior. Now, let's go back and revisit the domain question. So the domain says that it was x belongs to all the real numbers except 0. Now, let's really look at what's going on here. This is just saying that if you look at all the x values that satisfies this rational expression, everything is good except 0. So I'm a little bit curious. Let's kind of examine the behavior, right? I'm going to say the near behavior of the graph as you approach x equal to 0. We know that 0 is not part of the domain, but we want to know what happens as I get closer to 0. And so if I put 0 on the number line, I know I'm not supposed to get there. This is 1, that's 2, that's -1, that's -2. Then we can look at what happens as I get close to 0. This is from the right. And we normally denote it by 0 with the positive at the top. And then I also want to know what happens because I can approach 0 from 2 different places. And this is from the left. And we denote that with a 0 with a minus at the top. I want to know what's happening when I approach 0, either from the right or from the left of that value where it's undefined. So let's examine that. So again, we're going to try and pick some numbers that are really, really close. So when we talk about 0 minus, I want you to start thinking about numbers that are really, really, really close to 0 from the left. From the graph, from the number line that I have over here, do you think -1 and 0 are close or they are further apart? Well, your guess is right. They're very far apart because between 0 and -1, there are infinite amount of numbers between 0 and -1. So when I'm talking about a number that is really, really close to 0 from the left, I hope you're thinking about something like 0.001, negative 0, -0.00001, etc. So if I have these examples, let's just use them and see. So if I have f of -0.001, if I plug it in, I get 1 over -0.00001. I end up getting 1, 2, 3. I end up getting -1,000. And then if I try doing -0.00001, I end up getting -1 over 0.0234. I get 1, 2, 3, 4, 5. I get 10. I get 100,000. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. All right. So it looks like as we are getting closer and closer from the left, these y values are getting bigger, approaching close to negative infinity. Whereas if I tried 0 plus, you could think about it this way. Numbers that are really, really, really close to 0 from the right, you can look at 0.0001, 0.00001. I mean, I'm trying to get numbers not in any sequential order, but I'm looking for numbers that are really, 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 really close. All right. So again, if I test this out, I'm just going to use a similar one that I used over there. I have 0.001. Then I get 1 over 0.001. I get 1,000. And then if I do f of 0.00001, so I end up with 1 over 0.00001. Get 1, 1, 2, 3, 4, 5. You can clearly see again that y is getting bigger, approaching positive infinity. So we are seeing that as x approaches 0 plus, y approaches positive infinity, and when x approaches 0 negative from the left, y approaches negative infinity. Describes the line x equal to 0 as a vertical asymptote. From a graphical perspective, this is what we are saying. That I examined this location of the graph x equal to 0. All right, right here. And coming from the left, it told us that the graph was going to negative infinity. And then coming from the right, as x approaches 0 from the right, it told us that the graph was behaving like that. It was getting closer and closer to positive infinity. So what we've discovered is that we now have this line so that it didn't really work out, but we can certainly use a different color. This line over here where I get close to as I come from the right and the left of x equal to 0 is what we are calling the x equal to 0 is the vertical asymptote. They are both equations. All right, so both the horizontal and vertical asymptote are equations of lines. So you need to show in your work that you have x equal to a number or y equal to a number to describe the asymptotes. So big themes that came out of these two examples, looking at horizontal and vertical asymptotes, are these. Big ideas. When you divide 1 divided by a big number, it approaches 0. All right, and this happened when we analyzed for the horizontal asymptote. And then we just saw that when I do 1 divided by a small number, we approach either positive or negative infinity. And this was when we analyze for the vertical asymptote. So you're thinking about this in this way when you, like big themes that came out. When I do 1 divided by a big number, I get 0. 1 divided by a small number, I get what? I get positive, negative, infinity. So if you have your rational functions and you're trying to figure out horizontal asymptotes, you're trying to plug in a big number, both positive or negative, to see what the outcome will look like. If it goes to 0, you have discovered the vertical asymptote. And likewise, if you wanted to know if those exceptions in your domains are vertical asymptotes, then all you had to do was just check with small numbers to see what it is, to see if it's going to positive or negative infinity, so that you can claim that you have found vertical asymptotes. Later on, we'll come up with some more sophisticated ways to address this issue. But for now, these big themes should resonate with you on how we address horizontal and vertical asymptotes. So now we have all the ingredients to sketch. All right. So this is what we got. All right. I have a horizontal asymptote at y equal to 0. I have a vertical asymptote at x equal to 0. There are no x and y intercept. All I know is that as I get close to this y equal to 0, the graph could be doing this or that. Or it could be going there or there. And then I also know that if I am getting closer to this vertical asymptote, I am either this or that or this or that. Now, to sketch it, there are two possibilities. You can either rely on your prior knowledge, which is you know the graph of 1 over x. So clearly, it has to pass through here and go there. Oh, it's going to go do this and go do that. If that wasn't clear, then you'd have to do some test values on this region. And this region over here to see if the values are above the x-axis, or you do the same thing on the other side to see if the values of y's are below the x-axis, so that you can have a rough sketch of what the graph should look like. All right, so that's our first video, and hopefully this makes sense. In the next video that I'm going to show you, we're going to walk through some examples, and that should solidify what we just did today. Thank you. See you in the next video.